Hello. My project is on using a cellular automaton called Langton's ant in a very novel way to perform image encryption. If you're familiar with Langton's ant, you know that it's a cellular automaton on a two-dimensional grid of cells, and each cell can be either white or black. I'm going to consider a generalization of Langton's ant where I allow multiple colors. So instead of just black and white, let's say that I allow 4 colors now. I'm going to allow black, dark gray, suppose that's dark gray, light gray, and white. And I'm going to have a rule set associated with this. So let's say that I have the rule set left, right, left, right. What that's going to mean is that if the ant is on a black cell, it's going to turn left, update the cell color to the next cell color, which is dark gray, and then move one step forward. Similarly, if my ant is currently on a dark gray cell, it's going to turn right, update the color of the cell to the next color, which is light gray, and then move one step forward, and so on. Now it turns out that even if you start this on a completely empty grid of cells, some very complex and chaotic behavior can emerge. And so an idea that I had a couple years ago is, can we use this to encrypt an image? So I'm going to take a grayscale image, so for example this girl with a pearl earring, and I'm going to first downscale it a bit. So here I've downscaled it to 63 by 63, and I'm going to quantize the pixel values, so here to only 4 different pixel values. I'm going to run my Langton's ant for a large number of iterations. What's very, very interesting is if you run it for long enough, the resulting image basically just looks like noise. However, you can then run the ant in reverse, because you can reverse all of the rules that I described, and so from this image that just looks like noise, you can actually recover the original image. On a technical note, if the ant hits an edge, it's going to wrap back around. Let's have a look at what this looks like. I'm going to start the ant in the middle of the image, and I'm going to let it run with the rule set LR. Okay, now let's speed things up a little. And you can see that very quickly, the pixel values are turning into noise. It's basically can't tell what image this came from. So the main question that I want to answer about this is, how good is this as an encryption algorithm? And I've broken this question into 3 sub-questions. The first question that I want to answer is, if I as an attacker have the encrypted image, can I glean any information about the original image? So to answer this question, I'm going to look at the mutual information between the cells at t time steps into the encryption compared to my original image. Because each cell only has 4 different states, I can just use a discrete mutual information estimator here. And on the bottom left-hand side, I've plotted these results as a function of t. The blue curve here is what I just described, where I start off with the girl with a pearl earring, and I compute this mutual information quantity as a function of t. You can see that the mutual information seems to decrease quite quickly, and it approaches 0. What I also did is, I also did the exact same thing, but instead of starting with the girl with the pearl earring, I'm starting off with a random noise already. So for example, this image down here. So when it encrypts this image, it's still going to look like random noise, of course. The reason that I did this is I wanted to use this as a control point to see if there's going to be any kind of qualitative differences between, say, a more structured image or just random noise. Now, from the graph on the left, it seems like there might be some kind of qualitative difference between the two. To make this a bit more clear, I looked at the log of the mutual information instead. You can see here that when I start off with a random noise, which is indicated by this orange curve, it seems to go down a bit more quickly than if I started off with the girl with a pearl earring. However, at about, say, 100,000 iterations, both seem to start to flatline. And that corresponds to the point where there's basically no mutual information left. Something interesting about this plot is that once I look at the log mutual information, it seems to be roughly linear in both of my 2 cases. And so this would imply then that the mutual information seems to decay exponentially as a function of time. The second question that I want to answer is, how quickly does the image turn to noise? How fast does this ant scramble up all of the pixel values? So to do this, I need to have some measure of disorder. And the most natural thing to turn to is to look at entropy. But it's not enough to just look at the entropy of the cell values, because let's consider these two examples here. On the left example, I have 1/4 of the pixel values being white, 1/4 being light gray, 1/4 dark gray, and 1/4 black. And this has maximum entropy. However, on this image here, I also have roughly 1/4 of the pixels white, light gray, dark gray, and black. But clearly this right image should be considered way more random, or have a lot more disorder compared to this first image. But if I use entropy alone, both of these will give me the same entropy value. So entropy alone is not a very good measure here. And so what I decided to do is to look at a conditional entropy. I'm going to look at the entropy of a cell value conditioned on its 4 neighboring cells. Finally, let's discuss how I implement this estimator. So JIDT doesn't have an inbuilt conditional entropy estimator, but that's okay because I can actually use the chain rule to express mutual information as a unconditional entropy minus a conditional entropy. And so I can estimate my conditional entropy by instead estimating the unconditional entropy and the mutual information, and these are two quantities that JIDT does have support for. Finally, I have plotted at the bottom the results of this experiment. You can see that when we start with the girl with a pearl earring, the conditional entropy is quite low, and then it increases. And it seems to flatline at this maximum entropy value. On the other hand, if I start off with random noise, then the entropy is already at its maximum. And even as I run my ant, this entropy isn't going to increase any further. And once the cells are basically completely random, the 4 neighboring cells don't tell me any information about the center cell. And so if you look at these two variables here, they're basically independent, and so this mutual information goes to 0. And the conditional entropy then just reduces down to the unconditional entropy. Because if all of the cells are roughly random, then this is going to be log 2 of 4. So this is equal to 2. And we do see that this maximum entropy value seems to be just below 2. The final sub-question that I want to answer is, if I as an attacker have access to the encrypted image, but I try to decrypt it with the wrong rule set, so what's going to happen in that case? So I have encrypted my image with the rule set LR. If I get one of the characters wrong, and I try to decrypt it using that, what's going to happen? Am I going to be able to glean any kind of information about the true decrypted image using my incorrect rule set? To answer this question, I'm again going to look at a mutual information. I'm going to look at the mutual information between the encrypted image t steps into the decryption process. So this is my xt, and I'm going to compare it to t steps into the decryption process if I use the incorrect rule set. So that's my x prime t. Again, I've plotted this, and at this time we see that the behavior between the two is basically identical. Again, on the right, I've taken the log of the mutual information. What you can see is that after about 30,000 iterations or so, the mutual information seems to flatline. But before that, the mutual information, or rather the log of the mutual information, seems to decrease linearly. So this again seems to suggest that this mutual information decreases at an exponential rate. So what can we conclude? So for the first question, we can conclude that the information between the encrypted image after t iterations and the original image seems to decay exponentially in t. For the second question, we can conclude that after about 100,000 iterations, the encrypted image is indistinguishable from noise as measured using conditional entropy. Or at least this is the case for our toy example here at a resolution of 63 by 63 and 4 colors. Finally, for the third question, we can conclude that the information between the correctly and incorrectly decrypted images after t iterations also seems to decay exponentially in t. Some future work could involve measuring how robust these findings are to other images using the same size and the same number of states. Another line of work is to consider how does changing the image size or the number of states affect our findings.